Hi everyone, welcome back. I'm going to show you how to read the uh, result of a simple linear regression uh, that was produced by Python. And so the results includes a variety of robust statistics that I may have not covered well while running and analyzing for linear regression using Python, but I thought it would be a good idea to dedicate a whole session to demonstrate uh, how you can read or make sense of those statistics that you produce as an output of your analysis. So as you can see, this is the output of a simple linear regression. Of course, it's a simple linear regression because there is involvement of two variables, an IV variable, meaning independent variable, and a DV variable or dependent variable, where the IV independent variable is SAT score and dependent variable is GPA. So with this test, what we intended to do is to predict, well, first see the correlation between SAT scores and GPA, and then predict SAT GPA scores based on given SAT scores, and then also see if that relationship is statistically reliable or not. So I'm going to explain these findings using these stats numbers that are on the screen here. I'm going to start with the dependent variables and also during the a couple of disclaimers here. I will probably not cover fully a couple of these because they really require a separate detailed sessions, but I will try to at least touch upon what they really imply. Second disclaimer is that this is a view or the format of what the outlook or display would look like for a linear regression in stats models. So the package that was used or the module that was used to deploy this analysis in Python is called stats models. So if you use any other module or package and to deploy the same analysis, you will probably get a different result. I'm sorry, you would not get a different result, but you would get a different layout or different formatting of the stats. So, and so just wanted to make sure, as long as you're able to understand what each of these statistical concepts or tests mean, then regardless of the format or layout of the statistical outcome, should be able to easily understand uh, the findings that it tries to communicate with you. So the first one is the dependent variable. As I said, the dependent variable in this test is a GPA, where we are analyzing for correlationship and prediction for the GPA as the dependent variable using the independent variable of SAT scores. And it's simple linear regression, meaning that we are testing between two separate variables. Second one is the R square or R square coefficient. And so the R square coefficient is very important to know because it actually tells you how much you can rely on the independent variable as a predictor of your dependent variable. So an R square coefficient means how much of the data variation can be explained in the DV using the IV. So let's give the example of SAT. Let's use this scenario of SAT scores impact on GPA. So if the R squared coefficient is 0.406, that means almost 40.6% or 60% of the um, of the variation and the DV can be explained by the IV. So what about the remaining almost 60% or 59.40% of the variation? How can they be actually explained, right? That's the kind of question that the R squared coefficient can actually give you. That okay, if only 40% of the variation in the dependent variable can be explained by the IV, then what about the other 59.40%? So that's when, as a data scientist or a statistician, you actually think about introducing an extra variable here, or introduce an extra a covariable, or a confounding variable that actually add to this prediction to better explain the DB or the GPA. So is the SAT score out of high school enough for someone to have higher GPA in college? Um, yeah. So according to this test, that variation can be explained by 40.6 per 60 uh, percent, or 0.406%, right? And so, what about the other? Maybe we need to introduce, we need to analyze and review other variables that may be, that may better explain this entire analysis. Maybe the student's age, or maybe the student's number of siblings. Let's say maybe students specific exam scores on, let's say, mathematics. Maybe we can break down the SAT to other subjects, or maybe the students IQ. So there are other crucial factors or covariables that actually be introduced to this whole analysis that can that can actually raise this coefficient uh, to higher score, and it also explains well how the this 40 points, this score, but also explains provides a comprehensive explanation of how we can effectively predict for the GPA. So I percentile this, or I made this, I convert this into percentage, but you don't have to necessarily look at this through a percentage, outlook. The R square goes from 0 to 1, where 0 is actually no variation can be explained by 0%, or zero variation can be explained by the IV and the DV, while 1 is like while 1 is the absolute explanation of variation in the IV, from IV into DV. You will most likely not get an absolute 1 or an absolute 0. So you would expect something between 0.1 to like 0.9. So that's something that you'd expect. In the actual science programs, such as, let's say, medical science, or physics, chemistry, anything that involves that nature of scientific research, the threshold for a good R square is around 0.7 to like 0.9 maybe. Um, but in the realm of social science, an acceptable R squared coefficient could be something between zero point 0.2 to like zero point 0.4 maybe. Anything above that is even better and welcome. But as is obvious, natural science um, knowledges, or field of research actually require more higher level of validation in terms of reliability of explanation of variation between two variables, and as opposed to social science, where social science could be studies of economics, or sociology, that kind of stuff. All right, so done with the R square. Adjusted R square is important to take into account when you have multiple IVs. So in this case, it's a simple linear regression, and you also don't see a huge difference. But if you are looking at multiple IVs, then you should look at this and compare the two, and see what the overall R square would look like, right? And then what the R adjusted square would look like. So adjusted square actually take into account any difference of, that would be born out of introducing that extra variable into the analysis equation. So they both are important to know, but adjusted R square is more efficient or more important to review while you have multiple independent variables. The method for this is the least squares. To understand the least squares or the model and the method is OLS, and the model is OLS, which is the ordinary least squares model, and the method is least squares. So just just uh, just in a nutshell, and with the simple linear regression, we are looking for the best fit model or best fit line, and we're looking at different components of the line, such as SSC, SSR, SSD, and these are advanced statistics minutia that's in the background of a simple linear regression that you really want to know, that are important in understanding the concepts behind these numbers. So, this is the best fit line, and and we have these data values around it, right? So the sum of squares of errors, and also the line that crosses from them. The idea here is for us to actually take into account the residuals, and also the errors or that are around the misfit line, and then try to see how we can closely align this line with those data points. And this is not a full and include a final explanation of the least squares. It's a whole lot of stuff, but I'm just giving that explanation for you to know where if we are dealing with the simple linear regression of x and y, and then if you see this line, then you have to understand that this goes from the constant to the slope, uh, and with all the data points, the idea is for us to find the line that best fits the model. So that's all. If statistics, if you have learned about ANOVA, then you would know what F statistics is. F statistics involves testing differences of variance between variables. Especially ANOVA is more for like multiple variables to test their difference of means or averages, or how much they vary. So in here, the F statistics actually tell us if these two variables, right, if these two IV and DVs are actually statistically significantly different in terms of their variance. So if they're not statistically significantly different in terms of their variance, then there's something we may not take into consideration. Maybe these both come from the same source. So these maybe both come from the same sample, or maybe we're looking at the same thing. That kind of puts us under the question of multicollinearity. Are we looking at the same data variable? Are we looking at the same concept here? So that's why it's important for you to run the well, which your model will do it already for you, because so it's important for you to understand that the reason the model is doing it for you is because it's making sure that it actually passes this F statistics test, that you are actually looking at different variables involved in the whole model. And so it's below 0.05 and 0.05. Remember, this is the thresh the cut point uh, for a lot of social science related uh, uh, researches and statistic tests. So, and this is below 0.01, and it's a scientific notation that tells you it's significantly lower than 0.0001. So this means that this if this statistic is reliable by this p-value, probability value, and it's statistically significant. So the date is something that the machine produces based on when the uh, the model was run, and then time, and then the log of likelihood. I'll have a separate video on logarithmic transformation of data variable, but leave these live just leave this at this point. Um, the only thing that as I said at the beginning of the video, there was some stuff that I will not be able to explain in this video just for sake of time, but the log likelihood has to do with the logarithmic transformation and how much these variables can actually be tested for their likelihood of log. And number of observation is 84, which means we have 84 records or lines of data points. uh, AIC, BIC related to the Python a model for the stats model. Uh, this degree of freedom for the residuals is 82. And residuals I explained earlier about how our models goes from mx plus b and then plus e, which is the residuals. So degree of freedom for residuals is pretty much the number of observations 84 and the degree of freedom for residuals 82. Degree of freedom for the model is 1, which is the total number of variables in this model is 2, one being IV, one being DV, so two columns, right? So the degree of freedom is n minus 1, which is a sample. Since a sample by statistic law, it always has to be n minus 1. Um, so the covariance type is non-robust, and also have a separate video on this one. But covariance is, again, kind of relates to the idea of F statistics, where covariance is also like checking for the covariability between IV and DV. How much do they covary? And it's important for these two to have different covariances, right? And again, because we want to make sure that they are not significantly related to each other in terms of coming from the same sample. We do want them to kind of shine up on each other to show the relationship. But in the meantime, um, we want their covariance. We don't want them to be covariable, meaning they're different from each other in terms of variability. This is the most important table in the entire model that you need to know. The constant coefficient is 0.2750. So again, I've explained in other videos, you will use this for any equation to solve for dy, the dependent variable. But just a review. Uh, this is the constant. So whatever number the constant will be, we will be putting that in the equation to solve for y. And standard error. Uh, Standard error is very important to know, especially if you're going to build parameters or if you're going to estimate sample sizes or build or designate margin of error. That kind of stuff. It's important. It indicates how much you know the standardized error score between you know what the data is and what the sample would be from the actual data. So the standard error is 0.409, which tells us that it's a high standard error, relatively higher, and that actually affects our CI, which is these two numbers. So the CI is actually, and I'll come back to p-value in a second. I want to explain CIs using the standard error. So the CI is the confidence interval, right? Each time that you run analysis, or if each time that you designate something using sample, if you each time that you study statistically a sample, then you also produce using the standard error, which again it's the error between the sample and the data. Using the standard error and using the margin of error, using the confidence interval percentages, you build something what we call confidence interval for lower boundary and upper boundary. So lower boundary, upper boundary. So in other words, how much how much confident should we be where this data would be between these two boundaries? So at CI at 97.5%. 97.5%. So what will it be? What would it look like in a lower and a lower boundary? And oh, sorry, I put boundary here. I should have put upper. So that's what happens when you're explaining something while you're recording it. Oh, I did it again. Upper. Sorry, that's what happens when you're writing something while you're recording yourself. All right, so we have two boundaries, right? And what this value would look like in a lower boundary, what it looks like in an upper boundary. So with a 97.5% CI confidence interval, this constant, okay, the M will be between minus 0 point minus this, and upper boundary will be this. So lower, upper. The same thing with the SET, and I'll come back in a second. So the T statistics is 0.673. This is a lower T statistics with a p-value 0.503. So for us to be able again to be able to reject and null hypothesis or accept our test as significant, we have to have lower than 0.05 in the field of social science. So this is 0.503, but constants again has to do with this line of slope. So it's not highly relevant or effective on our model because we're not using constant, and so we're interested in the x here. So even if this does not uh, pass the statistical test of p-value 0.05, we can leave it as it is. But very importantly, I forgot to mention about 0.025. At the beginning, I was a bit confused when I saw this because I thought it was between the confidence intervals of 0.025 and 0.975. Actually, this is a p-value. So we have not only do we have CI that's built around the parameter of 0.9 of 97.5 percentile, but it also have a p-value that is equal to 0.025, which is below 0.05, right? So with the p-value 0.025, we can be 97.5% confident that our lower boundary for this coefficient will be 0.538, and our upper boundary for this constant coefficient will be 1.088. And how do we get this information? Using the standard error and also using this this confidence interval margin. Same thing with SAT. So our SAT is going to be our is going to be our oh, 1 second, is going to be our X. So this will be SAT. Yes, I forgot to put that actually B is our constant. Right? And this is going to be our SAT. All right. Oh, sorry. This will be our SAT. Oops, sorry. This will be our slope. I'm sorry again. Sometimes I just lose it when I'm recording and lecture. So as I said, we have the constant, which is b, x, which is the number that we independent variable that we assign or that we predict for, and then we have the slope, which is 0.0017. So the slope for the SAT is again the CI confidence interval is at 97.5% with a p-value of 0.0025 with a lower boundary of 0.01 and an upper boundary of 0.02. So if we predict let's say a GPA of a student to be, let's say, with a to be 3.4, right? but then we can be but then we can change this to the boundaries of let's say we uh, but before we get the final result, we need to minus these numbers from the actual slope coefficient and then multiplied by the x and then added with the constant. So this number will change. So this number will probably go from like, okay, with a 97.5% confidence interval with a p-value of 0.025, which is statistically significant. Well, you have a surprise. Your score may go from 3.1 to 3.7 maybe. So So not only do we get a predicted value, prediction of a value, in this case GPA, using a independent variable, but we can also build a parameter, a confidence boundary around that prediction to actually say how confident we could be to say where that number lies between this lower boundary and upper boundary, if it makes sense. So that's very, very important, not only with the linear regression, but for anything that involves samples and involves sample data and the population data, it's very important for you to familiarize yourself with the concept of confidence interval. And so when you build a confidence boundary around any sample statistics, it makes your work stand out with more reliability because you have something to refer to say because statistics is not always the final prediction of a given problem. You actually you always don't give a final result to say, okay, the prediction for X is 3. That's almost impossible because this 3 will never be permanent, a final 3. So it's important uh, to provide a kind of interval of where that 3 will be statistically and also with confidence parameters, if it makes sense. And so the p-value is below 0.05. It's 0.00, maybe goes to infinity or maybe to 1. But t statistic is 7.4, which is a higher t statistics. And the standard error is almost 0 point, it's almost below, it's almost, I don't even know because the model only shows the 3 decimals, right? So this is very low. This is very, very low statistic. So standard error statistic. So that's why we have, such a small margin of the difference in intervals value points. All right. So and then the last portion is this portion. It has to do with the data, and it's funny how we have the last portion as we have the last portion that we need in the first portion is listed in the last portion because this portion has to do with our overall quality of data and its normalization and what the shapes looks like for the data. So an omnibus test is also called a combined test. It's an overall test for a whole group of results. So, for example, an ANOVA, an F test, is a type of omnibus test. So, if you reject the null hypothesis, for a difference in variance, then one pair may have significant differences, or all pairs may have significant differences. That's why it's important for you to run an omnibus test to see okay, is this something that's only seen in one of the variables or two of the variables, or is something that's seen across all of the variables? So that's what the omnibus variable actually does, and we reject the null hypothesis here with the 0.02, which confirms our F statistics that says that the variables in consideration for the test are actually different. The second one is Durbin-Watson. The Durbin-Watson is also a test statistic used in the statistics to detect autocorrelation in the residuals from regression analysis. So pretty much we're looking for the autocorrelation. Um, as I said earlier, we want to make sure that we're not looking at the same variable and the variables are not autocorrelated. So the test actually goes from 0 to 4. So a value of with a value of 16, with a value of 0.950, we can be sure that uh, that uh, we can be sure with that there is actually no autocorrelation. But if it exceeds 4, then we can suspect that there's autocorrelation. Then we need additional advanced tests to really decipher this autocorrelation problem that we detect here. And then the other one is the Jarka-Bera or JB test. So the JB test, the Durbin-Watson test does not give you a p-value, so that you can designate the significance using the p-value. It just gives you a coefficient, or it just gives you a number that again falls between 0 and 4. But JB gives you, not only gives you a coefficient, a result, but also gives you a probability, just like other tests that we saw here. So what does Jark-Bera test tells us? Uh, the Jark-Bera test it's a test for normality. So normality, again, as always say, it's there are 4 or 5 assumptions that need to be actually tested and checked at the beginning of conducting a simple linear regression, and we need to make sure that all of those assumptions are actually validated for us before we even do the analysis. So it's one of this is a normality test, just like just to make sure that that's usually run before the test to confirm the normality. It's usually used for large data sets because other normality tests are not reliable when the n, which is the when n is large. So, for example, when the n is like, let's say, around 2,000 samples, then maybe we can do Shapiro test. But in this case, if the n is greater than 2000, then we need to do the Durbin-Watson test. That's a good test for any any data set with where the n is larger. In this case, the n is only 84, so I don't know why Python actually runs this test. Maybe this is not a reliable test to do. So specifically, the test matches the skewness and kurtosis of data to see if it matches a normal distribution or not. The data could take many forms. A normal distribution has a skew of 0. So as you can see, and this ties to skewness and kurtosis as well. So in the discussion of normality, it's important to know the two concepts of skewness and kurtosis. So skewness is, it actually tells you if this was a normal distribution, right? And so a minus skewness will tell you that the left tail, the left side of the distribution is actually dragged to the left, something like that. So that means that this is leftly skewed, or this is like negatively skewed, and that's what the number actually tells us. But since this is not a high number, right? This is not a highly skewed data set, but it does have a little bit of negative skewness to it. It won't be something like this. Maybe it's something slightly skewed like this is what we're expecting from this distribution where the analysis was conducted. So a normal distribution has a skewness of 0, and 0 actually indicates perfect symmetry. So this is a perfect symmetry, like a bill curve shape, something like that. I'm sorry, something like that. Yeah, a perfect symmetry like that. And so the kurtosis actually tells you how much data is in the tails and gives you, excuse me, an idea about how peak the distribution is. It's not necessary to know the mean or the standard deviation for the data in order to run the test, but so the kurtosis, again, the kurtosis actually looking at the peak. So the higher this number is, the more you have the more data you have distribution in the peak of your distribution. So with that, so if a number have a small kurtosis coefficient, then we're looking at something like this. If a number has a higher kurtosis coefficient, then we're looking at something like this, right? So it talks about, where this it's all about where the data points are gathered. That's what they're trying to indicate here. So since the Durbin-Watson test actually, sorry, the JB test explains that this is a normal distribution test, or this is a normal data set, or the variables are normal distributed, then we don't have to worry too much with the skewness or kurtosis, but it's always better to make sure that we include these in our uh, result on our paper, so that you know whoever's reading our paper or analysis knows what the shape of the data are in terms of their skewness and kurtosis peak. So con number, I don't even know what this is. Maybe there are some stuff like AIC, BIC, and con number that I actually these are like more like Python product uh, that came with the analysis that I've never seen with R or SPSS before. Uh, but the most important things that need to be covered for the purpose of understanding the a simple linear regression is important that I was just explaining to you. Uh, Thank you for your time, and have a great rest of the day or night.